All right, so week 3 went over forces. So this worksheet is on forces, utilizing the 3 different laws that Newton gave us. Right, so for number 1, draw a force diagram for a box that's being pushed horizontally on a frictionless table. Okay, so let's draw out a force diagram. Obviously, that's what the question is asking. So let's draw out our table. It's always nice. It's always good to draw a force diagram for your problems. It helps you sort of orientate what's going on. Okay, so we have our table and our box. Okay, so we got our box. Okay, so what forces are being applied to this box? Well, we have one force that's pushing the box horizontally, right? So I can do it in either direction. It's not specified. So I'm just going to put an arrow going this direction. Okay, so force of push. It's good to label what your forces are too. What else is acting? What other forces are acting on it? Well, there's one force that's always acting on every object, and that's gravity. All right, so gravity is in the y direction. So I'm gonna have it going straight down towards Earth, right? The force of G, force of gravity. Okay, and then we have the force of gravity acting on this object, but our object's not moving, right? So we need an equal and opposite force to gravity. And what is that? That's the force of the table pushing back up on the box, right? So we call this the normal force. So Fn for the normal force, right? Our box is only moving, or it's only being pushed in the horizontal direction, not moving the vertical direction. So we're going to have a balanced force in the y-axis. Right. So number 2, a stalled car is being pushed on a road with 300 newtons of force at a constant speed. Car weighs 1,360 kilograms. What is the acceleration of the car? What is the net force on the car? And what force is the car exerting on the people pushing the car? Okay, so let's go through this. So A, which is the first one, what is the acceleration of the car? Okay, so we can get this from like the problem sort of gives us a hint. All right, so a stalled car is being pushed on a road with 300 newtons of force at a constant speed. Right, so we know that acceleration is the measure of the change in velocity with respect to time. We know that there is no change in velocity here. It's going at a constant speed. So therefore, acceleration is going to be 0 because it's going at a constant speed. Okay, so B. What is our net force on the car? Okay, so the net force on the car. So if the car's acceleration is 0 meters per second, what does the net force have to be? So remember the equation, F equals ma. All right. If the car's acceleration is 0, what is the net force going to be? The net force is going to be 0 because 0 times anything is 0. So the net force, F net, equals 0. Okay. And then C. Okay. So for C, the third question, what force is the car exerting on the people pushing the car? Okay. So what force is the car exerting on the people pushing the car? So we know that F net equals 0, right? So if we do our equation, so we have F net equals the force of push, the force of people pushing, plus the force of the car pushing back, essentially. Force of the car pushing back on the people. Okay, so we know that F net equals 0, right? So the force of the push, we know that the car is being pushed at 300 newtons, or with 300 newtons, right? So that must mean if F net equals 0, that the force of the car pushing on the people has to be also 300 newtons, right? So negative 300. So negative is just the direction. So it's pushing backwards, right? So the force of the car exerting on people is 300 newtons. Okay, so this is sort of like, might confuse some people that our F net equals 0, right? So all our forces oppose each other and balance out to equal 0. So we don't have a net force, but our car is still moving. So again, this all comes down to the rate at which it is moving. So we know that since it's a constant speed, our acceleration is 0. So that tells us that all of our net forces are going to still oppose each other and balance out, but our car can still be moving. So just keep that in mind when you're doing your problems. Okay, number 3, a Prius accelerates from 0 to 26.82 meters per second in 12.4 seconds. What force does the passenger of mass 8 kilograms experience during the acceleration? Okay. So what force? Okay, so we want to know the force that the passenger experiences, right? So let's write down that equation, F equals ma. Okay, so we know the mass. We want to know the acceleration at which the car is going. Okay, so that's the whole thing here. We want to find out how fast or what the acceleration of our person is so that we can know what car or the force that is acting on the passenger. Okay, so how do we find that? Well, we can kind of dip back into those previous equations that we learned, right? The one really good one here would be v equals v naught plus acceleration times time. Okay, so we have all of those factors, right? We have the time, we have our velocities, and that'll give us acceleration, right? And that makes sense with the units too, because the initial velocity is 0, final velocity is 26.82, right? And then plus acceleration times 12.4. So if you look at the units, essentially what we're doing here is we're just going to divide 12.4, take it to the other side. So we're doing 26.82 meters per second, and then we're dividing it by seconds, 12.4 seconds. So that's going to give us meters per second squared, right? Which is the acceleration. So a good thing to do is to make sure your units are working out here. Okay, so that gives us an acceleration. Like a good way to check is checking your units. So this is our acceleration that we get when we do that. Okay, so now we have our acceleration, and we plug our acceleration in our equation. So F equals 68 kilograms times 2.154 meters per second squared. Okay, when you do the math, our force is 146.487 newtons. Okay, there you go. So our passenger is experiencing 146.487 newtons of force, essentially. That's what's going on. All right, so number 4, a car that weighs that much at rest rolls down a 20-meter long ramp that is at a 30-degree angle relative to the horizontal. What is the speed of the car at the bottom of the ramp? Okay, so a good thing to do here is draw out your diagram. Let's draw a nice big diagram. Okay, so car, we got our car. Rolling down a ramp, okay. And our ramp is, what, 30 degrees, I said? Yeah, 30 degrees relative to the horizon. Okay, so we want to know the speed of the car at the bottom of the ramp. So ramp is 20 meters long. All right, it's 20 meters long. Arrow. Okay, cool. So we have everything. We want to know the speed of the car. So how are we going to find the speed of this car? So what forces are acting on our car at this moment? We have, so it starts at rest, right? So the initial velocity is 0. What forces are acting on it? Gravity is acting on it, right? So I'm going to draw my force diagram. So the force of gravity is acting on it, and then force normal. right? The normal force, which is the ramp pushing the car up so that it doesn't go through the ramp. Okay, so we have those out. And essentially what I'm trying to do here is I'm going to use these forces. I'm going to break up the force of gravity into its x and y variables, right? So this is the y variable. I'm going to define sort of this as my x-axis, and then the force normal is like my y-axis. I'm going to break it up into this force of gravity into x and y variables, okay? And I'm going to find how fast this car is accelerating down this ramp. And then I'm going to plug it into one of my the previous equations that we've learned in this class to find the final velocity, right? So we can find the force of gravity. Like what is the force of gravity acting on this? Well, if you do F equals ma, we know that the car weighs, right? So F equals ma. We know that the car weighs 1,360 kilograms, and we know that the force or the acceleration due to gravity is 9.8. Okay, so then our force is going to be 13. Is that 3 or 2? 3.28 newtons, right? So that's what this is right here. Okay, so now I want to break this into its x and y components. Specifically, its x component here is what I'm really worried about. It's what I really want to get. So how do I do that? Well, I have this sort of this length right here, right? I want to find this length. I know that this angle of the triangle, one thing that you should understand is this angle that I draw right there, I'll draw in color. This angle is just going to be the same angle as this. So it's going to be 30 degrees, right? So it's always going to be the case. This angle, like right beneath the car that I drew, is going to be the same angle as our ramp. Okay. So now we know that this is 13328 newtons. So we can use some trigonometry to find what this is, right? Our force in the x direction. Okay. So so what are we going to do? So, right, SOHCAHTOA, right? Remember that. So in this case, it's opposite over hypotenuse. So it's going to be sine, right? We're going to use sine. So sine of 30 equals opposite, which is what we want, over hypotenuse, 13,328 newtons. Okay, so then when we do the math, then the opposite angle or the opposite length, which I'm just going to change to be x, just to make it more clear. X is going to be 6,664 newtons. Okay. So our force in the x direction, right? This arrow right here is 6,664 newtons. Cool. So again, let's go back to F equals ma. We know the mass of the object. We know the force that is acting on it in the x direction. Now we can find the acceleration. Right. So again, the force in the x direction, 6,664 equals the mass 1360 times acceleration. Okay, and when we solve for acceleration, the acceleration in this direction is, or in the x direction is meters per second, 4.9 meters per second, right? So our acceleration here is 4.9 meters per second squared. Okay, so now we got our acceleration. We have, let's write down our givens. Let's write down what we have. So we have the initial velocity, which equals 0 meters per second. We have how our displacement, right? Because the ramp is 20 meters long. What else do we have? We have now acceleration we calculated. So it's 4.9 meters per second squared. We don't have the time, but that's okay, right? We have equations that factor out time. And we want to find the final velocity. Okay, so we do know an equation that we can plug all these numbers into and get our answer, right? V squared equals V naught squared plus 2 times acceleration, x minus x naught. Okay, when we plug our stuff in, V squared equals 0 plus 2 times 4.9, and then our displacement is 20, right? So then when we solve for our final velocity, we'll get around 14 meters per second. Okay. Okay. Number 5. So determine the tension in the rope indicated. Okay, indicated by the star. So all the ropes and the pulleys are massless, and all the objects are at rest. Okay. So A. So what's the tension in rope A? So we can calculate this by finding the force this block is, the force that this block is exerting on the rope due to gravity, essentially, right? So our block weighs 15 kilograms. We know again by F equals ma that the force that is exerting due to gravity is 15 times 9.8. So that force is 147 newtons, right? Okay. So the force going down is 147 newtons, right? And so just understand that since the block isn't moving, right, let's say this force going down, so force of gravity is 147 newtons. Now understand that because the block is at rest, that means there's an opposing force of 147 newtons on it, right? So the opposing force of this 147 newtons is going in the upwards direction, right? Because our block isn't moving, 147 newtons. So the opposing force is that sort of like tension force that this rope is applying to the block, right? So the tension in this rope is going to be 147 newtons, right? And it's anchored to the ceiling, right? This little wall up here. So essentially, the wall is applying 147 newtons of force in the upwards direction, which will balance out the block, which is applying 147 newtons in the opposite direction. Okay, so the net force of this object is 0. Okay, so B, we got 2 different ropes that I want to talk about. So this first one right here, what we have is essentially we have a 15 kilogram block on one side, and then we have 10 kilogram attached to a 5 kilogram block on the other side of this pulley. This is a pulley. So essentially, this 15 kilogram block has a force due to gravity of 147, right? It's the same as the one up there, newtons. So it's pulling down with 147. Essentially, the one on the other side, right, we have a 10 kilogram block attached to a 5 kilogram block, and that's below this rope, right? So this rope is bearing the weight of the 10 and the 5 kilogram block. So that's important because essentially you can combine these two, and both of them are going to be pulling down with an equal and opposite force of 147 newtons, right? And that makes sense because our blocks aren't moving, right? So essentially the tension in this rope is going to be 147 newtons. Okay, so this is very similar to the first one, right? Except we sort of have like a counterbalancing weight instead of the wall just supporting the rope or supporting the blocks, right? So in the first one, the wall or the ceiling was pushing up with 147 newtons of force to balance it out to get an F net of 0. And this one, we just have another block that is bearing that weight and is pulling down with an equal and opposite force. Okay, so the tension in this rope is 147 newtons. what is the tension in this rope down here that is holding the 5 kilogram block? Okay, so this 5 kilogram block, let's write sort of what's going on. It's not moving, right? So I know that F net equals 0. It's going to be pulling down with a force of gravity, right? So 5 times 9.8, which is, where is it? It's 49 newtons, right? So I should have known that, 5 times 9.8. Did I do my math right on that? Let's check real quick. 5 times, yeah, 49. Okay, so 5 times 49. And then again, the block's not moving, so the force going up is also going to be 49, right? So that tension force in this rope is 49 newtons, okay? So just don't get confused. It's not going to be 147 newtons like this one up here, because it is only bearing the weight of this block, this one block down here. So this particular rope is only bearing the weight of this block, whereas this rope, right, is bearing the weight of both the blocks. So it's going to have a different force to it. Okay, so C is slightly different. We are no longer looking at this rope. We're looking at the rope attached above it. Okay, so now this rope is bearing the weight of both of those blocks. Okay, so the force of gravity on this rope, essentially it's just supporting the pulley, right? So the pulley has 10 kilograms attached to it. So the force of gravity, if I write sort of right here, pulling down with 10 times 9.8, so 98 newtons, okay? So then we need a supporting force, because nothing is moving here, of 98 newtons in the opposite direction. So the tension force needs to be 98 newtons to support it, essentially. And again, if you guys have any questions, just comment below. Okay, so last one. A 20 kilogram block is resting on a table. You pull the block attached to a string upwards at a 40-degree angle relative to the horizontal plane. How much force do you need to pull the block to lift it off the ground? Okay. So let's draw a little diagram of what's going on. Got our block, 20 kilogram. Okay, being pulled. This is, it's on ground, right? Being pulled to whatever direction you want with a 40-degree angle, right, to horizontal. Okay, so the rope is at a 40-degree angle to horizontal. We don't know how much we're pulling. That's what we want to find, right? We want to find out how much force we need to apply in this direction to lift the block off the ground. Okay, so what do we need to know here? Well, we need to know, first of all, how much force is being applied to this block due to gravity, right? So we need to know that force. And let's do that real quick. So, right, F equals ma. Gravity, acceleration due to gravity is 9.8. 9.8 times 20 is 100. So the force of gravity is 196 newtons. Okay, we also have a normal force here that at the moment is 196 newtons, right? Force, that's normal. Actually, I shouldn't write that. We have some sort of normal force here, right? Whatever it may be, whatever, right? So how much force do we need to apply to this block to lift it out, or to get it to lift off the ground? So we have our rope that's attached right here, right? It's pulling at a 40-degree angle. So the first thing that we should do to find this is essentially we need to find how much force we need to apply in the y direction, right, to get it to lift off the ground. Okay, well, we know if the force of gravity, the force due to gravity is 196 newtons. We have to overcome that force. So we need at least to pull it upwards with 196 newtons. Okay, so if we pull it upwards with 196 newtons, it will start to lift off the ground, right? So perfect. Now we just have to find out how much force we need to apply in this diagonal direction to get 196 newtons in the y direction. Okay, so it's just a matter of trig now. So we do sine of 40 equals what, 196 over the hypotenuse, which is what we want to find. So x, and this, let's say this is x. X is 304.92 newtons in this case. So we have to pull this rope in the diagonal direction with 134.92 newtons of force in order to get 196 newtons of force in the y direction, so we can lift our block off of the ground. Cool. Yeah, if you have any problems with this material, feel free to comment or come to my office hours. They are posted on iLearn. And yeah, good luck. I know you guys have your test coming up soon, so good luck with studying and all that stuff.